to a session on relation between Boyle temperature and critical temperature. In this session, we will be deriving an equation showing the Boyle temperature and critical temperature. Let us move on to this topic. It is a relationship between Boyle temperature and critical temperature. Boyle temperature, we usually denote it as TB and critical temperature as TC. The equations are TB is equal to A by RB. This is previously derived in previous sessions, and TC is equal to, we just saw it, it is HA by 27 RB. So, comparing these two, see here we have TB is equal to A by RB. Okay. And TC is equal to 8A by 27 RB. Okay, I will take another color. Okay. Now, here you can see that TB is equal to A by RB, see. And in TC, we also have the expression A by RB, right. These two are common. What does it mean? This A by RB you can substitute as TB. This can be substituted as TB, right, because TB is equal to A by RB. Now, we will back to the calculations. See, I am going to write the expression as now TC is equal to, here 8 and 27 are left out. So, 8 by 27 into TB, because A by RB is TB. Now, I am going to represent it in terms of TB, that is TB is equal to TB, I will retain here, when this 27 is taken to other side, since that is in the denominator, it goes to the numerator 27, and 8 being in the numerator, that will go to the denominator. So, 27 by 8, and we have the TC over there. So, this becomes the relation between Boyle temperature and critical temperature. Boyle temperature TB is equal to 27 by 8 TC, where TB is the Boyle temperature and TC is the critical temperature. Now, dividing 27 by 8, just do it in a calculator, you will get it as 3.375 TC. Now, taking the ratio TB by TC, because TC is taken to this side, it comes to the denominator, TB by TC is equal to 3.375. This is the calculated value, and experimental value, when we have found out the ratio of TB by TC is approximately equal to 2.5, and theoretical value is 3.375. So, there is a slight difference in these two values if we compare. Okay. Now, this discrepancy is because theoretical and experimental values is, and again if you calculate the value of set C also, there is a deviation from the theoretical value. This is because we have an assumption that in Van der Waals equation, the Van der Waals constant A and B are taken, calculation we are taking it as their constants, but actually they are not constant, they are temperature dependent factors. Okay, that is one reason for having this discrepancies, and A and B values are determined from critical data, and therefore actually that is applicable only in the vicinity of critical temperature and pressure. So, that is the difference we find in the theoretical and experimental values for both ratio of TB to TC, as well as if we calculate the value of critical compressibility factor. Okay. Now, this, if it is in the critical conditions, we will have all these values to be approximated or somewhat corresponding to or very much nearer to the theoretical value. Now, these are some of the values of PC, VC, TC and ZC are given. For gases, hydrogen, nitrogen, oxygen, carbon dioxide and helium. See, PC, VC all are given whatever it is. Now, ZC, that is critical compressibility factor. Of course, that is critical. It is under critical conditions. Compressibility factor and TB values are given here. You can see that the value of ZC is 0.305 and here it is 110.0, which is the Boyle temperature. Okay, here the Boyle temperature is 0.292, the Boyle temperature is 327.2. At that temperature, the compressibility factor is 0.29. Again, here it is 0.308, it is 0.274. For helium, it is 0.305. See the values, and the expected value is approximately 2.5, and what we got by calculation is 3.375. Okay. So, the values, they are very much varying even when we take it at the Boyle temperature, where we believe gases tend to be ideal. Okay. Next, we will move on to some of the problems. The van der Waals constants for oxygen are A equals 0.1378 Newton meter raised to 4 mole raised to minus 2, and the value of B is equal to 3.18 into 10 to the power minus 5 meter cube mole inverse. Now, assuming oxygen behaves as a van der Waals gas, calculate its critical constants. We are assuming that to be obeying van der Waals gas equation, and therefore, you can calculate the critical constants. Now, the data given are A is written here, B is given, that is all taken from the question. R is not given in this problem, and according to the units taken. See, these are the SI units, and therefore, the value of R should be in SI units, that is R is equal to 8.314 joules per Kelvin per mole. I have already mentioned in previous sessions that taking R, it is not necessary that they will be giving it, but it should be chosen according to the units which they are provided. Okay. So, here it is R is equal to 8.314 joules per Kelvin per mole. Now, we are going to derive one by one. Vc is equal to 3b, that is the expression. Pc is equal to A by 27b square, and Tc is 8a by 27rb. First, we will evaluate Vc because that is very easy, that is equal to 3 into b, 3b, b, the value of b is 3.18 into 10 to the power minus 5 meter cube mole inverse. Okay. So, just multiplying, 3 into 3 is approximately 9. So, the answer will be 9.54 into 10 to the power minus 5. The unit will be same, that is meter cube mole raised to minus 1. So, that is the answer for Vc. We have found out the value of Vc. Next, we have to find out Pc. So, A is given, A is equal to 0.1378, this is all data provided, newtons meter raised to 4 mole raised to minus 2, and B is equal to 3.18 into 10 to the power minus 5 meter cube mole raised to minus 1. And the expression for Pc is equal to A by 27b square. Just substitute the values and solve for it. A is equal to 0.1378 newtons meter raised to 4 mole raised to minus 2, then whole divided by 27, okay, b square, that is equal to 27 into 3.18 into 10 to the power minus 5 meter cube mole raised to minus 1, and that is a square factor. Do not forget, it is square. Okay. Now, solving, you will be getting the answer as 5.047 into 10 to the power 6 Newton meter raised to minus 2. That is, just take the units. This is, here it will be meter m to the power 6, here mole raised to minus 2. Mole raised to minus 2 and mole raised to minus 2 get cancelled. Meter raised to 6. When I take to the numerator, it becomes meter raised to minus 6, and here we have meter raised to 4. So, we can cancel it here, it becomes 2, and meter square taken to the numerator, it will be meter raised to minus 2, and newtons, of course, it does not get cancelled. So, Newton remains there, and the unit will be newtons meter raised to minus 2. Hope it is clear. Now, next is we have to find out TC. TC is equal to 8A by RC. These are the data taken. Okay. 8 into A is equal to 0.1378 Newton meter raised to 4 mole raised to minus 2. Okay. Whole divided by 27 into R. R is equal to 8.314 joules Kelvin per mole. Then B. B is 3.18 into 10 to the power minus 5 meter cube mole inverse. Okay. Here Kelvin will be there, mole raised to minus 1 and mole raised to minus 1. 2 mole raised to minus 1 cancels, mole raised to minus 2. Meter cube, here we will have to take it as newtons per meter, and that get cancelled with joule, and here goes, there is only m to the power 3, and this and joules, and one of the meter gets cancelled, and this meter cube also gets cancelled over there. So, meter raised to 4, and finally, you will get the answer in Kelvin. Solving for this, the answer comes as 154.4324 Kelvin. So, that is the answer for TC. Okay. So, first we have found out a VC, and then PC, and finally TC. All the three critical temperature, pressure, all the three critical constants are calculated. Next is again another problem. Here we have PC, VC and TC of chlorine are 76.1, this is PC. Okay. Next is VC, that is 0.124 decimeter cube mole inverse, and this will be TC, that is 417.2 Kelvin respectively. Calculate the van der Waals constants A and B. Now, here I have written down all the data. PC is equal to 76.1 atmospheres, VC is equal to 0.124 decimeter cube mole raised to minus 1, okay, and TC is equal to 417.2 Kelvin. Now, R, the universal gas constant, is not given here. Now, here again while choosing R, since all these are in liters and atmospheres and decimeter cube means that is liter, okay. So, all these are in this unit, we have to take the value of R in liter atmospheres. So, that is 0.0821 liter atmospheres per Kelvin per mole. Now, one more factor to be noticed, we can easily find out the value of B using this relation, but if you calculate, you can take your time and calculate for yourself, you will get a different value for VC when it is calculated from this value, and you can also find out the value of B from VC, and if there are these are two equations showing relation between PC and TC, and these two relations, they give a different value for B. And it has been found that if we take these two together and evaluate B, that gives a more accurate value than calculating B from this. So, it is better, we will not be using this, please note that we will not be using this to calculate B, we will be using these two relations to find the value of B, because the value of B is given a more appropriate value or more exact value when solved from these two equations. So, here what I am going to do is I am going to take the relation PC divided by TC. Now, why I am taking PC divided by TC? Because in this both the equations, if you check, both has the value of A as well as B, but here B it is in square and here it is simply B raised to the power 1. So, from this I can get B, and here you can cancel the terms A. So, the remaining van der Waals constant by taking the ratio will only be B, and therefore, we can calculate B from that relationship. So, PC is equal to A by 27B square. Okay. Now, divided by TC means divided by 8A by 27RB goes to the numerator. So, that will be 27RB. Now, we can cancel the common terms. See, A and A will get cancelled. Okay. B goes 1 times in B square, so it becomes B. 27 and 27 gets cancelled. Okay. So, what is remaining is here we will have R, 8 is there, B is there, R is there. These are on the, that is equal to, I will just put it here, R by 8B. Okay. Now, here actually we are supposed to calculate B. So, I will make the expression as B. So, B I will take it to this side, which goes to the numerator. So, B is equal to, we have taken to this side. I am bringing PC and TC to the other side. When B is taken, the remaining is R by 8, that is on the left hand side, and from right hand side, from left hand side I am going to take PC and TC to the other side. PC being in the numerator goes to the denominator, and TC being in the denominator goes to the numerator. Now, I will substitute the values 0.0821, that is R, temperature is 417.2 Kelvin. So, you can put the units too, that is liter atmospheres per Kelvin per mole, whole divided by 8 into PC, that is equal to 76.1 atmosphere. Okay. Now, here just check the values, K inverse and K gets cancelled, liter atmosphere get cancelled. Okay. And solving for this, you will get the answer as 0.05626. Liter means that is decimeter cube. You can put it in any way, you can put it as liters per mole inverse, that is also okay, or you can put it as decimeter cube per mole inverse, it makes no difference. So, first remember, while calculating B, never calculate it from Vc is equal to 3B. We will calculate B by taking the ratio of PC to TC, because that gives an accurate value for B. Now, once the value of B is obtained, you can substitute that in any of the above equations, that is either in PC or TC, which you find convenient. You substitute the value of B in that and calculate the value of A. So, here I have taken this equation, that is just because here we do not have any squares or anything. So, the calculation will be more easy. So, I have taken TC is equal to 8A by 27 RB. TC is given, that is from the data, R is given, B we have calculated as 0.05626 decimeter cube per mole, or I can put this also as liter, okay, it does not matter. Now, I am going to substitute Tc is equal to 8 into A divided by 27 RB. Now, this is what we are going to solve for A. So, I will keep A on one side and take the rest to other side. So, I will keep A on one side. Now, taking 27 and RB, which are in the denominator, will go to the numerator. So, on the other side I will be having TC into 27 RB. Okay, this goes to the numerator. Now, 8 I will be bringing to the side, because that is in the numerator, it goes to the denominator, divided by 8. Okay. Now, the value of Tc is 417.2 Kelvin into 27 into 0.0821 decimeter cube. Instead of liter, I can put it a decimeter cube, atmosphere per Kelvin per mole, multiplied by B. What is B? Point that we have already calculated, 0.5626 decimeter cube per mole, okay, divided by 8. Okay. So, here Kelvin inverse cancelled, decimeter cube and decimeter cube can't cancel, they are on the same side, mole decimeter 0.0 Kelvin per mole, mole raised to -1 and mole raised to -2 makes mole raised to -6, decimeter cube and decimeter cube becomes decimeter raised to 6 and the atmosphere as such. So, the answer will be in units of atmosphere, decimeter raised to 6 and mole raised to -2. On solving, the value comes as A is equal to 6.5037. So, that is the value obtained for A. Hope it is clear. Please note that for getting the value of B, we never use the relation Vc is equal to 3B, though it is Vc. Just divide Vc by 3 will give you the value, but that is totally different. You won't be getting this answer for that. Okay. Next is, I am providing an assignment which I will be discussing in the next session, that is van der Waals constants for nitrogen are A is equal to 1.38 atmosphere decimeter raised to 6 mole raised to -2 and B is equal to 0.0391 decimeter cube mole raised to -1. Find the critical constants that is Vc, Pc and Tc. You are supposed to find out all these three and note that I am not giving the clue, just note the units used and choose the R properly. Okay. To conclude, let us go through, that is first we have derived a relationship between Boyle temperature and critical temperature. You can see that Boyle temperature, it is given by the expression A by RB, Tb is equal to A by RB. and the critical temperature is given by the expression Tc is equal to 8A by 27 Rb. Now, here when I write these equations, see, on Tc, we have 8A by 27 Rb, where A by Rb represents Tb. It's a very easy derivation. A by Rb represents Tb, and therefore, I can substitute A by Rb as Tb. Okay. So, that becomes A by Tc is equal to 8 by 27 Tb. Okay. And keeping Tb on one side and taking the others to the other side, I get Tb is equal to 27 by 8 Tc, and taking the ratio, that is Tb by Tc, it becomes 27 by 8, or by solving we will get it as 3.375. Okay. The experimental value is approximately 2.5. It is highly deviating from the theoretical value, and this value is deviation occurs just because in van der Waals equation we assume that A and B are constants, and they are not at all exact constants for a gas, and they vary with temperature, or you can say that A and B are temperature dependent, and the datas of A and B when taken at the critical conditions, it's almost okay, otherwise it deviates. Okay, in the vicinity of critical conditions, it's okay. And next one, what we have done is that we have been seeing that A and B are not constants, and they remain constant only near the critical condition. And that is a deviation we find because this value is experimental. Tb by Tc is equal to 2.5, that is around 2.5, that is the experimental values. Okay, and these are the relations we got. Tb is equal to 27 by 8 Tc, and Tb is equal to 3.375 Tc, or Tb by Tc is equal to 3.375. And that's all for this session. Thank you.